how we characterize growing these things by physical vapor transport. We're going to identify our host material by LIBS, XRD, Raman, and FTIR. And then finally, we're going to establish the ideal chromophore that's going to be doped in these metallocene. So, and then we're going to go over a little bit of wrap up and future projects. So, the motivation for single photon sources. Single photon sources are going to be a core kind of component into really cool technologies like quantum computing, quantum communications, and quantum circuits. Although these single photon sources are not going to be the main component of these, they're just going to be integral. So it's a part that's going to build on these processes. So just very brief, quantum computing, you can do parallel processing, very fast computation speeds. You can do complex modeling. Quantum communications, it's increased efficiency of communication efficiency. It has some weird quantum mechanical effects, quantum indeterminacy, there's a no cloning theorem to do with this. You can't copy messages, you can't detect eavesdroppers. And a core piece of these two is photonic circuits. They're more efficient, less heat, generally be a better device all around for everyday use. However, so all of these things currently, some of us have seen maybe some quantum computers. They are very large devices. They require a lot of expensive equipment. You can't put one on your phone, per se. So our part to facilitate a smaller device would be, we're going to focus on making photonic, or making single photon sources at room temperature. A list of single photon sources. So there's 4 main photon sources. We can do a single defect. Single defect's been studied a lot. Quantum dots. This is also a well-studied system. We have single molecule. So single molecule, it's kind of one of the more newer iterations of this, and a trapped ion or atom. Each one of these has their own disadvantage. Defect states, implied in the name of defect, they are very sparse or even one defect in a lattice material. So in this case, you would need an array of these to even make a bright emission. Also, replicating the defect is, as implied in defect, very hard to do. Quantum dots are very bright emitters. However, they're made of a bunch of semiconducting materials interacting with each other. They have what's called less coherence. So coherence is the how long the state of the quantum dot it can produce. Molecular ones, they are bright also emitters due to the symmetry of them, and have a large transition dipole moment, meaning that, like, depending on the axis of rotation or vibration, you have a stronger emission. And we have trapped ions and atoms. They require very strong, very coherent, very stable lasers to hold a single atom. So in our group, we're going to focus more on the molecular emitter. And so the core idea is, in the molecular emitter case, although it's bright, these are organic based. On their own, they can decompose due to oxidation from the environment. So our core idea is we take these metallocene single crystals. These are organic based in nature. They have a cyclopentadiol carbon ring on top and bottom with a central metal ion. And we will take these chromophore emitters. Chromophore meaning that the energy absorbed or emit in the visible spectrum. So the core choice between these two is these are very well studied molecules. Actually, ferrocene was first accidentally synthesized in the 50s, and out of ferrocene, they quickly synthesized niclocene and cobaltocene. And these chemicals here, they actually started some rift in chemistry where everyone was confused on how to classify them. And a guy won a Nobel Prize in 1973. So these guys are also very well known, very well studied, very documented in literature. So with the basis of using these two systems, our core idea is we're going to take chromophore and insert it in a single or single crystal. So why is that? So the idea is each one of these metal ions arranged in this crystal lattice will form what's called a Faraday cage. Now, a Faraday cage, any outside interference or in magnetic interference or electrical interference will be shielded from the chromophore. Another cool thing about these Melusine crystals is that they're separated by a van der Waals distance, because of the distance comparatively large, to shield it from the environment and vibrations. So, all right, given the host matrix and given the chromophore, we need to determine out of all of the selected metallocenes which will be best. As I should have pointed out earlier, notice why these three. There's actually many, many more metallocenes like rutheniacine. There's even one with a uranium atom in it. Can't name it off the top of my head, but naturally these will form the magnetic shielding because they have a high magnetic permeability to it, in like natural iron, cobalt, and nickelocene. So, how do we prepare these samples and make them? We use a physical vapor transport. Now, physical vapor transport is not the only way to make these metalloceine crystals. You could use solution growth, or you can do vapor growth. However, PVT makes ultra high pure crystals. And this is due because there's a secondary purification process in the PVT. And this PVT process works by you have a gradient oven, so a higher temperature in the center, lower temperature on the outside. We have an argon gas, or inert gas, that flows through the, like a quartz tube. The ferrocene will subliminate from the solid phase into the gaseous phase. And once it reaches to a cooler region, it will condensate it back into the crystal form. Each chemical or material has its own sublimation temperature and also condensation temperature. So this method can separate heavy impurities and lighter impurities, resulting in a very pure metalloceine single crystal. Okay, so going through that process of describing how these metalloceine
Is it, you say 150 Celsius? Isn't it too low?
So, yes, actually, so if you look up in the literature, you'll see the temperature of ferrocene and nickelocene and metalloceine, they're much higher. But in this case, your crystal growth and your crystal size is determined on this temperature parameter. So the nucleation energy, or the nucleation is given and governed by the flow rate and the temperature. The lower the temperature, you can make a much bigger crystal and have low nucleation. It's more new crystals growing.
So it evaporates tiny amount.
Yeah. Also, another kind of intrinsic fundamental thing is the lower the temperature is, the more there's less thermodynamic energy in the molecules, so they have an easier time to attach without some point defects or line defects in the crystal. Any other questions? Okay. All right. So we're going to, out of those three metallocenes, we want to characterize them and determine ultimately which metallocene single crystal will be the best host matrix. We're going to do a couple of tests and measurements. Well, we're going to do XRD to determine crystal structure. We're going to do Raman and IR to determine the vibrational modes and properties of these crystals. And then, interestingly, the last one, I was deciding to put this one first to ruin the surprise of which one of these is the best, but I put it last. So to keep everyone engaged here. So, the first, one of the methods we use is LIBS. It's called laser-induced breakdown spectroscopy, which basically what you do is you take a laser pulse, and you shine it onto your sample. This pulse is powerful enough to ablate the material. Ablate means you remove parts of the material out of that single crystal. It turns that ablated material into plasma. So then when the pulse is turned off, that plasma, and those excited ions and excited atoms in that plasma, they'll fall back down to the ground state. Each element has its own deterministic band gap energy resulting in its own kind of photon that's generated when it falls back down. And we can characterize these emissions. And basically, what we determined is when it's grown by PVT, that the cobalt ions, nickel ions, and ferrocene ions